Unit 3, Chapter 2, Thermochemical Equations and Enthalpy Change Calculation. So, thermochemical equations, they have some distinctive features that differ them from a normal chemical equation, and you must demonstrate those features. So first of all, it started from a normal chemical equation, but then you need to add enthalpy change value to the right of the chemical equation. For example, in the perspiration equation, so our body turns glucose when there is oxygen available into carbon dioxide and water. Yeah? This reaction releases energy, and that's how we keep ourselves warm. So the enthalpy value is written on the right-hand side of the equation. Yeah? So you can see that the unit of enthalpy change is kg per mole. So it does matter how much of the reactants are actually there. So here, the coefficient of this reactant is 1, and therefore the value is negative 2,803. If I multiply the entire equation by 2, the delta H value has to also be multiplied by 2 as well. Okay? And also, the states of an equation is important. Okay? So when you are asked to write a thermochemical equation, make sure that you add states to every single of the substance in the equation. Okay? And that is simply because absorption or state changes involves absorption or release of energy as well. So for example, when water goes from liquid to gaseous, it will have to absorb energy itself as well. So the delta H value will be affected in that situation. So we need to tell people when delta H is this value, what we actually mean, what are the states of the reactants that contributes to this value. So the 10th table on your data book gives you a list of delta H values, basically. They call them heats of combustion because they don't come with a positive or negative sign. So when you are writing a thermochemical equation, make sure that you add positive or negative as per circumstances. So if it's a combustion reaction, then it will release energy, then delta H value will be negative. Yeah? And also, it gives you a definition. All those delta H is defined at standard lab condition, which means your water will be written as liquid. Okay, so if you're actually using delta H from your data book, make sure your water is liquid. And of course, your oxygen is always gaseous. Okay? So, unlike math, even when delta H is positive, make sure you always put a positive sign before it. It cannot be omitted. So the calculation of delta H. If I ask you to use a data book to write a thermochemical equation for the complete combustion of ethane, how would you write? Okay, so some of you would have written this equation, which is correct. So you directly take the delta H value from the data book, and if that is the case, you need to make sure your coefficient of the fuel, that's the combustion substance, is 1. Okay? So our data book gives you the delta H value when all of this is 1. All of your fuels has to have coefficient of 1. In that case, your oxygen will be written as a fraction. Is that allowed? Yes, it is. And that is, you normally permitted when you are writing a combustion reaction, or we say when you are using delta H values from your data book. Right? So what if I have written as in this equation? What do I do? Well, as we've said, you only simply need to multiply the delta H value by 2. Okay? And since delta H for a combustion reaction, it's a negative. What if the reaction is reversed? Then your delta H value will be reversed as well. It will become positive. So if the forward reaction releases heat, then the backward reaction will intuitively absorb energy. Give it a try of this equation, this question. The combustion of hexane takes place according to this equation. So consider here. We can see that the target equation is simply the equation given, but it's written in reverse. Okay, it's a reverse reaction. And at the same time, the coefficient of the target equation is doubled as compared to the original one. So how to calculate our delta H for the target equation? We simply need to reverse the delta H. Okay? We add a negative in front of it, and we times the entire thing by 2. So the answer is A. Hess Law. Hess Law is actually very useful because it's something that we discovered through experiment. We realized that the enthalpy change for the overall process will be identical regardless of how many steps are taken. That means as long as your reactants are the same, it's A plus B, and your products are the same, plus C plus D. Yeah? But whatever steps you're taken, so you can go from A to B, A and B, straight away to C and D, or you can go through multiple steps, which are a lot of times required by chemical production. Yeah? But your enthalpy change overall will remain the same. So this equation is very useful. Delta H1 equals to 2 and 3 and 4 added together. You don't need to take away or do anything about it. Whether it's positive or negative, you just have to add all the values together and you will get the overall enthalpy change. Okay. How is that useful? Let's try this question. They give you the energy profile of these two equations, yeah, two reactions, and they ask you for the delta H for this dubious reaction. What is this? Well, if you look closer, you realize that actually this reaction is somehow the combination of these two. You have copper 2 oxide here, you have copper 1 oxide here. Yeah? It seems that if you somehow reverse this reaction and somehow manipulate here to get rid of this fraction here, you might be able to find the final equations here. Yeah? Now let's label these two and do a simple mathematical manipulation. You realize the overall reaction is simply the reverse of this reaction, the first reaction, plus the second reaction, but times by 2. Yeah? And then you cancel out the same thing on both sides of the equation, you will get the final equation. So you only need to do the same thing for delta H. Yeah?